Hello and welcome to this video tutorial on the computer side of the CRP5. Now this is in essence a circular slide rule. A slide rule is a powerful computational calculation device that was used to send rockets to the moon during the Apollo program and navigate Soviet nuclear submarines during the Cold War. But we're going to use it here to carry out various calculations in the world of aviation. Now, the essential design principle of this thing is these two circles of numbers, an inner dial and an outer dial. And each number is separated from every other number by a fixed number of degrees. That number of degrees pertains to a particular multiple. Let me show you what I mean. So there's the number 10, and if we go around the circle we find the number 20. 10 times 2 is 20. Those numbers are about 108 degrees apart. You can measure it. And that angle of 108 degrees also separates 20 from 40, or 30 from 60. Basically what we say is move that number of degrees around the circle and you will have doubled the number you first thought of. Therefore, the essential operating principle of using this thing is that we're going to line up the inner and outer dials such that the inner dial multiplied by something equals the number on the outer dial. We can do this with some basic multiplication. Let's have a go at a sum that I dare say most of you can probably do in your heads anyway, but 2 times 3. It's just going to make the point. So, basic multiplication. Inner times something equals outer. In this case, I'm looking at 2 times 3. So what I want to do is line up the inner and outer so that every outer number is 3 times the inner number. There's number 1 on the inner, so I'm going to line that up with the 3. I can do that. 1 times 3 is 3. So there we go, 1 and 3 lined up. And now every number on the outer dial is 3 times the number on the inner dial. If I want to know what 2 times 3 is, it's 6. 2 times 3. If I want to know what 3 times 3 is, there it is, 9. 4 times 3 is 12, and so on. So it turns out that 2 times 3 equals 6. Hopefully most of you knew that already, but you've seen this thing in operation. What if the numbers get a bit more complex? What if we're looking at, say, 13 times 47? Well, what we're going to have to do is a little bit of mental approximation. And that's to do with the limitation of the CRP5's computer side. The numbers only go up so far. What we have to understand is that in the case of, for example, the number 60, as it is displayed here, that can represent 60, but it can also represent 6, or 600, or 6,000, or 60 million, or 0.6, or 0.06. It all depends on the order of magnitude that we're searching for. So here your mental math skills will allow you to approximate the answer so that you know what order of magnitude the answer should fall into. In the case of 13 times 47, 13 is around 10, 47 is around 50, 10 times 50 is 500. So I'm looking for a number in the hundreds, of the order of 500-ish. I can go a little bit further with that with my approximation. I don't know 13 times 47 in my head, but I do know 3 times 7. And 3 times 7 is 21. So whatever number this is, it definitely ends in a 1. The last digit of this number is a 1. I'm probably looking for a 3-digit number. Let's have a look at this in action then. 13 times 47. So, 13 times 47. Once again, everything on the outer should be 47 times everything on the inner. So, there's the number 47. I'm going to point the 1 at 47. So now, 1 times 47 is 47. 2 times 47 is 94. What's 13 times 47? Well, here's the number 13 on the inner. 13 times 47 would be, well, 61 and a bit. Well, that doesn't seem very likely. That's why I have to do the mental approximation first. 13 times 47 is a bit more than 10 times 50, so around 500 or so, something of that order. I also know that 7 times 3, being the last two digits, give me 21, so the last digit of this number ends in a 1. So something around 500 or so, 600 makes sense, 610 and a bit, ends in a 1, must be 611. Okay, so that's basic multiplication on the CRP5. But of course it can do far more sophisticated things than that. Have you ever noticed just how many different systems we have for measuring things in aviation? There are reasons for that, and they are broadly historical. Allow me to give you a very brief summary. This island, which we now call Britain, developed over centuries, if not millennia, a system of measuring things. Based on whatever we had lying around the place. You know, the size of my hand, the length of my arm, how far can a Roman legion march in 1,000 paces, that sort of thing. And we eventually standardised. The basic unit of length was the inch. 12 inches gave us 1 foot, 3 feet give us 1 yard, and if we ignore all the intermediate rods, poles, chains, perches, furlongs and what have you, 1,760 yards gives us the mile, or if you prefer 5,280 feet, the statute mile, that is, the mile measured over the land. We also did a similar thing for mass. The basic unit of mass was the ounce, it's about that much. 12 ounces, don't be ridiculous, 16 ounces make up the pound. And similarly with water, if we measure out enough water that it weighs an ounce, we call that a fluid ounce, and 16 fluid ounces became the fluid pound, which we shortened to pint. Meanwhile, we then have the gallon for larger volumes of water, which of course is 8 pints. Why wouldn't it be? And then the British invented sailing. Measuring distance over water proves a problem, because of course Roman legions don't march across water, so we had to come up with a different way of measuring distance whilst at sea. What we did was we took the entire circumference of the Earth and divided that into 360 degrees, each of those degrees into 60 subdivisions called minutes, and 1 minute of travel around the circumference of the Earth we called a nautical mile. Turns out that it's around 6,080 feet, which is slightly longer than the 5,280 feet of the statute mile. Now, one of the places that the British people sailed to was, of course, the Americas. And having settled in America in the early 17th century, passed on the standards of weights and measures to the Americans. By now, the British were starting to form an empire, and so these became known as imperial measurements. This is where things started to go just a little bit wrong, because whilst the Americans were happily using these standard measurements, the British, under the reign of Charles II, decided pints weren't big enough, possibly something to do with drinking more beer, and so a pint became 20 fluid ounces. The gallon, though, was still 8 pints, which is why the imperial gallon is slightly larger than the US gallon. In order to make everything a lot less confusing, now we go across the English Channel to our French brethren. The French invented an entirely new system of measuring things, based fundamentally, once again, on the size of the Earth. You draw a line from the North Pole to the equator, which is a quarter of a way around the circumference of the Earth, divide that line into 10 million lengths, and you end up with the metre. 1 metre can be subdivided into hundreds and thousands, called respectively the centimetre and the millimetre, or multiplied by hundreds and thousands. 1,000 metres we call 1 kilometre. It's all based on factors of 10 and makes a lot of sense. For example, if you have your metre and you take 10 centimetres, 1/10 of a metre, get a box that's 10 centimetres by 10 centimetres by 10 centimetres. The volume now occupied that box is 1 litre. Fill that box with water and it weighs 1 kilogram, or 1,000 grams, which allows us to see straight off the bat that 1 cubic centimetre, of course, equals 1 gram. Excellent. But there was a problem. Britain was at war with France. Britain did not wish to adopt the French system of measuring things because it was a foreign power, and they were naturally fearful of this. They would put themselves at a bit of a disadvantage, but it was worth it to avoid having foreigners interfere in British affairs. Of course, that made a lot of sense during a time of war. Thank goodness we're beyond that sort of nonsense now. But anyway, the British won the Battle of Trafalgar, beating Combined French and Spanish fleets in 1805, and what that meant was that the French were forced to sell the bit of America that they still possessed. It meant that America became a former British rather than a former French colony, thus ending any possibility of the French metric system interfering with the American way of measuring things. Fast forward to 1903, the Americans basically invent aviation, and of course they use American measurements to measure most of their things. Meanwhile, much of the rest of the world has adopted the metric system, including the British, and of course we still have the maritime system for measuring distance over which we're flying. And so we have this situation now where we measure distance in nautical miles, except when we don't, because sometimes it's the distance we can see, visibility, which is measured in kilometres and metres, except when it isn't, when it's measured in statute miles. Our altitude is measured in feet, unless of course you're in a part of the world where they measure it in metres, and so on and so on and so on. And fuel gets a lot more confusing. Fuel is measured in mass in kilos, unless of course you're American, it's thousands of pounds. And its volume, what it's delivered to you from the Bowser Inn, is measured in litres, unless of course it's measured in gallons. What sort of gallons? US gallons or imperial gallons? Hard to say, and thank goodness there's never caused enough confusion to let a plane accident happen. But anyway, the CRP5 computer side deals with a lot of that confusion, allowing us to convert between any given unit of volume, any given unit of mass, and any given unit of length. Let's start with units of length. What we are going to have to do, once again, is do just a little bit of mental approximation so that again we know the order of magnitude that we're looking for when we develop the answer. So, some basic conversion factors. A nautical mile is very roughly a statute mile. A nautical mile is also, very roughly, 2 kilometres. A kilometre is 1,000 metres, that's a given. Therefore it is very roughly 1,000 yards. And a yard is 3 feet. That's pretty much all you have to know to be able to convert between these measurements using the CRP5. A basic understanding of roughly the number you're looking for, and then you can use the CRP5 to actually calculate the accurate answer. Let's look at a few of these in action. So I've been given here a certain number of nautical miles. So the first thing I need to do is look for the nautical mile mark. There it is. And of course the answer is not always going to be 54 nautical miles. So that should give me the hint that what I'm looking to change, of course, is on the inner dial. In this case, I'm looking at 25 nautical miles. So let's line up number 25 with the arrow as accurately as I can. There we go, that's 25 lined up with the nautical mile arrow. And now all the other distance and length markers around the outside are lined up with the requisite number on the inner dial. So I'm looking for around about the same number of statute miles. Well, there is the statute miles mark, and that would be approximately 28.8 statute miles. So 25 nautical miles is 28.8 statute miles. I know that it's going to be about half the number of kilometres, so I'm looking for something around 50 kilometres. Let's bring it round to 50. 46, 46.3. Yep, fair enough. Metres, well that's easy, that's just kilometres times 1,000, so 46,300. Yards is about the same as metres, so 50,000, and what's that, it's 6, so 50,600 I would say. And finally, feet are 3 times the number of yards, so around 150,000, indeed 151,000, just under 152,000, let's say 151,900 approximately. So there we go, I don't have to remember any of the conversions particularly, I just know roughly the conversion, and this helps me answer the question exactly. Okay, bigger numbers, 420 kilometres. Let's find the kilometres. There it is. 420 kilometres. Absolutely lined up. Now I know that about half the number of kilometres will be the number of nautical miles. So I'm looking for around 200 and something nautical miles. Here's the nautical miles arrow. 220 227 nautical miles, and about the same number, very approximately the same number of statute miles, 260, a bit less than 262, so 261 statute miles, I would say. Meanwhile, kilometres times 1,000 is metres, so that's easy, 420,000 metres. About the same number of yards, 400 and something thousand yards, which is just to the right of kilometres. There it is, 406, maybe just under 459,000 yards, and 3 times that will be that in feet. So it's going to be 1 million and something. 1,000,003, nearly 1,400,000, but let's say 1,380,000, maybe slightly less, 1,378,000, very approximately. There it is in feet. All right, so that's length, but what about volume and mass? Well, we actually need to remember very, very few basic conversions. They are very rough, very approximate, but they'll be good enough for using the CRP5. 1 litre weighs a kilo, or at least it does in the case of water. Fuel weighs a bit less than water, so 1 litre of fuel weighs around about 80% of a kilo. We say that fuel has a specific gravity of 0.8, that's what that means. But if I remember that litres and kilos are pretty close to each other, that's good enough for using the CRP5. And a litre, well, there are about 5 litres to the imperial gallon. And a US gallon's a bit smaller, so there's about 4 litres to the US gallon. Now, kilos, of course, are smaller, so if I'm converting directly from kilos to gallons, I'm going to have to factor in the specific gravity, at least when it comes to fuel. But broadly speaking, that's all you need to remember. Kilos and litres are about the same, and there are about 4 or 5 litres to every gallon. With that in mind, we can now use the CRP5 to convert between different volumes and between different masses, and even between volume and mass. Let's have a look at that one in action. So 500 litres of fuel, same sort of idea. Kilometres, metres, litres, they're all in the same place because the metric system is better. 500 of them lines up right there. So that's the 50, which we are interpreting as 500, lining up with the litres. Well, we can go a number of ways with this. There are approximately 5 litres to the imperial gallon. So let's look for imperial gallons. And we expect imperial gallons to be 1/5 of the number of litres, therefore. So just over, well, probably about 110. So 110 imperial gallons is my 500 litres. And US gallons are a bit smaller, so we're going to need more US gallons to make up the 500 litres. Probably around 132. So 132 US gallons, 110 imperial gallons, 500 litres. Now, when converting to kilos, litres to kilos, if it's water, it's just a straight conversion. 500 litres of water weighs 500 kilos, but fuel weighs a bit less. In this case, we're assuming that fuel weighs 80%, or 0.8 times the weight of water, and that means that I come over here to the kilo scale, select the appropriate line for a specific gravity of 0.8 and read off the inner dial, and it's 400 kilos. So 500 litres at a specific gravity of 0.8 becomes 400 kilos. What's that in pounds? Come round to this side, looking at the 0.8 arrow once again, and it's about twice the number of kilos. So if it's 400 kilos, it's 800 and something pounds, 880, maybe just a shade more, 882, I I think we can safely say. So there we go. So slightly bigger numbers here. We're looking at 10 tonnes, and it's 10 tonnes of fuel. So if it were 10 tonnes of water, 10,000 kilos of water, it would take up a volume of 10,000 litres. But it's fuel, which is lighter. In fact, in this case, we're going for 0.8 specific gravity. So 10,000 kilos at a specific gravity of 0.8 equates to slightly more than 10,000 litres. In fact, it's 12,500 litres. 12,500 litres, divide it by 5 and you get imperial gallons. So around between 2 and 3,000, something like that. So let's find imperial gallons. And reading off the inner dial, 2,000, pretty much in the middle, 2,750 imperial gallons. US gallons is going to be a similar sort of amount, slightly larger. 3,300, almost exactly. And finally, the 10,000 kilos in pounds is going to be about twice the number. Again, specific gravity of 0.8. And we have 22,000 pounds. 10,000 kilos is 22,000 pounds. At a specific gravity of 0.8, it's 12,500 litres, 3,300 US gallons, and 2,750 imperial gallons. There we go. Okay, temperature. There are 2 competing scales of temperature in use in the world. One of them is degrees Celsius and the other degrees Fahrenheit. Here is a map of the world showing all the countries that use degrees Celsius. And here is a map of the world showing all the countries that use degrees Fahrenheit. Yeah, okay, but it's still possible you might have to convert between the two. So there is a handy scale on the CRP5 computer side to allow you to do this. Let's have a look at this in action. Let's first look at what is 35 degrees Celsius in Fahrenheit. So not a commonly scrutinised gauge, this one, but it's a straight lineup. So if I'm looking at 35 degrees Celsius, that equates to 95 degrees Fahrenheit. That's it, straight across there. 35 Celsius, 95 Fahrenheit. And now that we've worked out, what about going the other way? What is 10 degrees Fahrenheit in Celsius? And similarly, 10 degrees Fahrenheit, it's on the bottom scale here, would be minus 12, just a shade colder than minus 12. So shall we say minus 12.2, something like that. All right. The CRP5 can also be used in terms of calculating our speed. Now, what fundamentally is speed?
Speed. I am speed.
All right, so Lightning McQueen is speed, fair enough, but speed is fundamentally distance divided by time. A certain distance in a certain time gives us our speed. That's where the magical 60 triangle comes in on our inner dial. On the outer dial, we're going to set the number of miles we're talking about, and on the inner dial, we're going to set the time in minutes. If I forget which way around it goes, bear in mind that the word minutes is actually written permanently on the inner dial. My speed, of course, is generally given in knots, but all that is nautical miles per hour. So if I'm giving the speed of, say, 500 knots, I set the 500 against the hour marker, and now I have 500 miles in 60 minutes, and I can read off how many miles I've done in how many other minutes. I don't even have to convert hours and minutes into straight minutes, because this yellow band here does that for me. So for example, 95 minutes, hopefully I should be able to convert. That's 1 hour 35, but just in case, yep, there it is on the yellow band, 1 hour and 35 minutes. Let's have a look at this one in action. Let's start by calculating what our speed is if I travel 400 miles in 1 hour and 20 minutes. So in this case, I'm looking for 1 hour and 20 minutes. There it is, which is 80 minutes. Probably I could have worked that out, but it saves me the bother of having to try. And I'm doing 400 miles in these 80 minutes. So minutes, which are always on the inside, there's minutes on the inner dial, must therefore line up with the 400 mark on the outer. So they go 400 miles in 80 minutes. So how many miles am I doing in 60 minutes? There's the 60 marker. I'm doing 300 miles in 60 minutes. 400 miles in 1 hour 20, 300 in an hour. In other words, 300 knots is the speed. Okay, and we can also go the other way, what we might call reverse engineering. If I know my speed is, say, 550 knots, I can work out how far I'm going to travel in 25 minutes. So in this question, we're coming at it a slightly different way. 550 knots means I'm doing 550 miles in 60 minutes, in 1 hour. Minutes are always on the inside. So 60 lines up with 550. There it is. And now the number of minutes lines up with the corresponding number of miles around the outside. So 550 miles in 60 minutes, that is 550 knots. And I'm doing 25 minutes only. There's 25 minutes, and it lines up with 229 miles. All right, so that's speed. In basic terms, how fast do we fly through the air divided by a certain amount of time? That would give us our true airspeed, how fast we are actually flying. But the gauge, the airspeed indicator on my aircraft, doesn't show me my true airspeed, it only shows me indicated airspeed. All this is a gauge attached to a tube on the outside of the aircraft which measures how much air is flowing into that tube. For a start, it's not a perfect instrument. There are pressure and instrument errors associated with it, but even if we could eliminate those and have a perfect ASI, that would only give us our rectified or calibrated airspeed, sometimes shortened to RAS-CAS. RAS-CAS is a useful measurement, particularly if we're calculating aircraft performance, but it is not our true airspeed. For a start, the faster we go, the more air is forced into that tube, and eventually the air itself becomes compressible. That allows more air in than there should be, and we get a slight overread. Eliminating that error, which we call compressibility, gives us our equivalent airspeed. The higher I fly, and or the warmer the air gets, the less air there is. The air is getting less dense. And therefore, once again, we're going to get an underread. Correcting for that error, the density error, finally converts equivalent airspeed into true airspeed. Now, the way the CRP5 computer side is going to come to our aid here is by using the airspeed window. Remember, the basic operating principle is inner dial multiplied by something gives us the outer dial if the things are correctly aligned. Well, in this case, the something is a combination of altitude and temperature, that is, density. By lining up the correct temperature with the correct altitude, we can then read the inner dial number, which is the RAS or CAS, and read the outer dial number, which is the TAS. Again, if we forget which one is which, it says RAS-CAS on the inner dial. It says TAS on the outer dial. But what about compressibility error, Owen? Well, let's panic about that if the TAS gets fast enough for compressibility to matter. That's the magic number of 300 knots. So let's start with a basic example where we're not worried about compressibility, we're just converting RAS-CAS, essentially our indicated airspeed, into our true airspeed. So these questions look complicated, but fundamentally it's still inner times something equals outer. It's just that the times something, in this case, is a combination of altitude and temperature. So that's what we're going to set first of all. The temperature is -20, and for this we're going to need our airspeed window, because what are we working out? We're working out airspeed. So if the temperature is -20, that's about there, and the altitude that I want to line up with that temperature is 20,000 feet. So I'm going to need to come round a little bit. So there's 20,000 feet. There's a temperature of minus 20. I'll get rid of the cursor so you can see it slightly more easily. So minus 20 degrees, between 0 and minus 40, and 20,000 feet is inside the window. Now the inner is lined up with the outer correctly. 160 knots, and if I forget which one is which, inner is indicated, and also rectified and calibrated airspeed is on the inner, TAS, true airspeed, is on the outer. So 160 knots on the inner lines up with 220 knots on the outer. In this case we're looking at a RAS-CAS of 204. So there's 204 knots of calibrated airspeed lining up with 280 knots of true airspeed. No compressibility to apply. That's the end of that. Okay, now we're going to try a higher speed example, and this time we are going to have to apply compressibility. The compressibility window is here, and what it essentially says is that if you line up the inner and the outer only accounting for density error, the outer number that you read off is going to be too large. You're going to need to move the inner dial slightly to the left to prevent that overread. How much to the left? Well, it depends. Take your true airspeed, divide that by 100, subtract 3, and that gives you the number of divisions you are moving in the direction of that arrow. I think rather than try and go through that again, it's best that we see this one in action. So with this question, let's just start the process. What do we know? 35,000 feet. So we're looking at airspeed, 35,000 feet, just there. And I want to line that up with a temperature of minus 64 degrees. So where are we? Minus 64 is about there. Okay. So now the inners and the outers are correctly aligned, at least for lower speeds. So 150 knots indicated would be close to 260 knots true. In this case, I'm told that the calibrated or rectified airspeed is 300 knots. There's 300 knots. And that equates to something like 510, about 518 knots of true airspeed. But that's a big number, it's more than 300, so I'm going to need to apply compressibility. If I forget that 300 is the magic number, the actual equation is given to me just here. So 300 divided by 100 is 3, minus 3, there's 0. But in this case, 518 divided by 100 is 5.18, minus 3 is 2.18. So I need to move this arrow slightly more than 2 divisions in the direction of the other arrow as such. So there's 1 division and there's 2 divisions. So now the 300 knots of CAS is lined up with 500 knots of TAS. All right, now, sometimes, of course, you're not given the outside air temperature, you're given it in the form of an ISA deviation. For that, we have to remember what the ISA temperature at any given altitude should be. You should know the formula by now to be able to figure that out. The CRP5 can actually show us how to do that, but we will have a look at that later on when we come to look at temperature correction for altitude. For now, just watch out. If it says ISA minus or ISA plus, remember you need to work out the ISA temperature first, then apply the deviation in order to give you the outside air temperature. Let's have a look at one of those. Right, so minus 41 is ISA temperature. However, it is ISA plus 10, so it's only minus 31. There's the first bit of the puzzle. It's minus 31 degrees and 28,000 feet. Over to the airspeed window. Minus 31 degrees lines up with 28,000 feet. Sort of like that. And now once again the inners and the outers are aligned so that RAS or CAS on the inside gives me TAS on the outside. In this case I'm looking at 250 knots of CAS, which is something like 396 knots of TAS, but that's more than 300. We're going to have to apply compressibility. 396, it's close to 400, divide by 100 gives me 4, minus 3 gives me 1, so I need to move this arrow 1 division to the left to about there. And now the 250 knots of calibrated airspeed lines up with 390 knots of true airspeed. Okay, so if you know the outside air temperature, you can work out eventually what your true airspeed is. What if we don't? What if we're only going off the indicated outside air temperature? Well, that's nothing more than telling me what the thermometer stuck to the outside the aeroplane is showing me. And the faster I go, the warmer the aircraft is getting, owing to skin friction. That's where the blue section of the CRP5 computer side comes in. It's the temperature rise scale. Firstly, we're going to assume that indicated temperature is truly outside air temperature and calculate our true airspeed on that basis. But then we're going to go to the blue bit. Apply the TAS, read off the temperature rise, and what that's telling you is how much of an overread is the indicated outside air temperature. How much colder, in other words, is the actual or corrected outside air temperature. Once I know the corrected outside air temperature, I can go back in and recalculate my TAS with that new information. And finally on this subject, there is the vexed question of compressibility. Once again, indicated outside air temperature, I need to calculate a ram rise. For that, I need to calculate a TAS. But for that, I need to apply compressibility. So I'm going to take that temperature, work out a TAS, apply compressibility, use that TAS to calculate a ram rise, then go back in and repeat the entire process with the corrected outside air temperature and compressibility once again, eventually to give me the true airspeed. Okay, here we go. End of level boss. Firstly, assume indicated temperature is actual temperature. So, temperature minus 25 and the altitude 34,000 feet. So 34,000 feet in the middle of the window, minus 25 on the outside. There we go, that's them lined up. Now the inner CAS gives me the outer TAS. 272 knots of CAS gives me 500 knots of TAS. Excellent. Except that that's not right, because compressibility factors in. 500 divided by 100 is 5. Minus 3 is 2. So I have to move the arrow 2 divisions to the left. 1, 2. There we go. So now 272 knots of CAS is approximately 478 knots TAS. But that temperature is overreading. How much is it overreading? Well, let's go to the temp rise scale. 478 knots is my current TAS. At 478, I'm getting a temperature rise of 25 degrees. So the temperature sensor, the indicated temperature, is 25 degrees warmer than the actual outside air temperature. So if it indicates minus 25, the actual outside air temperature is a colder minus 50. Because the ram rise, the temperature rise owing to my true airspeed right now is 25 degrees. Okay. Now I have to restart the process with the new corrected information. Temperature of -50 and an altitude of 34,000 feet. -50, 34,000 feet. Now those things are aligned. The actual outside air temperature is aligned with my altitude. 272 knots of CAS lines up with 472 knots of TAS, but again compressibility is factored in, so 472, that's 4.72 minus 3 makes 1.72 divisions to the left, probably about there, I would say. So the 272 knots of CAS eventually turns out to be 457 knots TAS. True airspeed, 457 knots. Now when it comes to measuring airspeed, we have our airspeed indicator, of course, but we also have the Mach meter. And in many ways this is more accurate because the Mach meter simply gives a percentage readout, which is your true airspeed as a percentage of the local speed of sound. Local speed of sound, as you no doubt know, is given by this formula here. And what that implies is that the only real variable is temperature. Mach number varies only with temperature and with true airspeed. If I know the true airspeed and the temperature, I can calculate the Mach number, and so on. The CRP5 computer side eliminates the need for memorizing this formula by using, once again, the airspeed window, but we're going to rotate the airspeed window until such time as this little arrow appears, the Mach number index. Point that at the correct outside air temperature. TAS is on the outer dial. It's still on the outer dial, it always is, that's why it says TAS there. And on the inner dial is a number representing the percentage of the local speed of sound. 100% is the local speed of sound, also known as Mach 1, 90%, 80%, 70%, and so on. So let's have a look at this. What would Mach 0.84 be if the outside air temperature is 0 degrees? So, Mach number. Mach number is a measurement of airspeed, but the only variable is the temperature. So I need to find that Mach number index little arrow. There it is. And I am told that the temperature is 0 degrees. So there we go. The local speed of sound then would be where the 1 on the inner. So inner is indicated. We're indicating Mach 1. That would be a shade over 640 knots. But I am told that I'm looking for Mach 0.84. There's 80. 1, 2, 3, 4. 84% of the local speed of sound is 540 knots of true airspeed. And if I forget which dial I'm supposed to be looking at, remember true airspeed is always on the outer. And again, watch out, we can always reverse engineer these. Sometimes you'll be given the speed and you have to work out the Mach number. Sometimes you'll be given the Mach number and you have to work out the speed. So once again, temperature is now -45. There is the Mach index. There's the temperature of -45. And 435 knots of TAS is there. And that lines up with a Mach number of 0.712334, 0.74. Sometimes you'll be given Mach number and speed, and you have to work out the temperature. It's all possible using the computer side of the CRP5. There's the Mach number index, but I don't know the temperature. I do, however, know the local speed of sound is 600 knots. So I'm looking for a TAS of 600. There's a TAS of 600, and the local speed of sound is Mach 1. So 1 lines up under the 600. Now, the inner dial, the Mach number, is giving me a certain percentage of the outer dial, the true airspeed. 100% of the outer dial is the local speed of sound, and the temperature at that point is wherever the Mach number index is pointing to, which is -35 degrees Celsius. There's two other windows available to you on the CRP5 computer side. One is rarely used, but it's this one here, density altitude. For takeoff and landing performance, we often need to know the equivalent altitude that our runway is at. Well, for this, we're going to use a combination of the density altitude window and once again the airspeed window. Line up the temperature with the airfield elevation, and the density altitude window will convert your airfield elevation into a density altitude. Let's have a look at a couple of examples. Density altitude. It's a bit weird because it uses the airspeed window. I don't have a good and effective way of remembering that. But let's say we are at 5,000 feet and it's 5 degrees at 5,000 feet. So there's a pressure altitude of 5,000 feet. There's a temperature of 5 degrees lined up. What density altitude does that equate to? A 5,000 foot density altitude. Good to know. However, if it warms up, so we're still at 5,000 feet, and now we're going to a temperature of plus 30, the air's getting less dense. My density altitude is in effect increasing, and indeed it has increased to around 8,000 feet. And the last little window is this one, the altitude window. Hopefully you already know how to correct for pressure error, that is when the QNH is anything other than 1013, but you also need to be able to correct for temperature. Here the general rule is high to low, look out below. If I'm going to somewhere where the temperature is lower than ISO, it means that my true altitude will be lower than my indicated altitude. The general principle, as with airspeed, is that what's indicated is on the inner dial. So just as an experiment, let's line this thing up perfectly. We've already eliminated pressure error. We're assuming that the QNH is 1013 and I've set 1013 on my altimeter. So the only error left is temperature. If there's no temperature error, what that means is that it's isotemperature. This is how we can use the altitude window to determine what the isotemperature should be at any given altitude. If the temperature gets warmer than ISO, then the inner indicated altitude is going to line up with a higher number on the outside because our true altitude is higher than indicated. It's a warm day, this is a slightly safer condition. The opposite, of course, is also true. Let's have a look at this in action. In this case, I've been told that it's 5 degrees at an indicated 11,000 feet. So there's 11,000 feet. I'm going to line it up with the 5, about there. And now the inner dial is the indicated altitude. So with 1013 set, my altitude on the dial is showing 11,000 feet, but I'm at a true altitude of 11,500 feet. And I would expect that because it's warmer than ISO, therefore I'm in a less dangerous position. So again, I'm told that it's minus 20 at 12,000 feet. So that's the altitude window. And now the inner indicates my altitude as being 12,000 feet. And the outer is the true altitude of 11,500 feet. So it's clearly a low temperature day because my true altitude is slightly lower than what it says on my indicated altitude. So there we go. That's the CRP5 computer side and all the various exciting things that it can do. Do watch out in the question for all the little tricks that can be played on you. Be particularly aware of the possibility of reverse engineering. Have you been given a temperature and an altitude, or are you expected to calculate one of those two things? But bear in mind the fundamental operating principle, what all the little windows are supposed to be for, and you can't be too far wrong. However, you'll probably need to practice. That's what this table is doing behind me. The purpose of this table is to allow you to practice. There are some questions, information has been blanked out, that's the stuff you're supposed to calculate. Once I've disappeared, this will stay here for 10 seconds, and then one by one the answers will be revealed. This allows you to pause the video at appropriate moments and work through at your own pace. By then you will have mastered the computer side of the CRP5, and you will be much the better pilot for it, I dare say. Thanks very much for watching. I wish you all the very best.